Oh, looks like we're live.
Okay, sorry. I'm sitting here talking. Well, let's start over.
I thought it was just me.
No, we're gonna start over. So welcome to Northwest Arkansas Coders monthly guest speaker meetup. We have the privilege of having Eric Burden with us today, who's going to be giving a talk on Rust. Real quick, I want to go over the goal of Northwest Arkansas Coders is to provide a safe place for people to learn, a community where people can speak about anything tech related and then life in general as well. We just want to provide a safe place and give people a place to get their hands on real projects and get real world experience, even if they haven't quite landed that job. But again, I want to present Eric Burden, and so here's Eric.
All right. Hi, good evening, everyone. Let me fix my mic real quick. That might be better. Tonight, I'm going to talk to you guys about Rust, the programming language, and we're going to do it from one of my favorite perspectives, which is solving coding puzzles. I find that coding puzzles are an excellent way to learn any new technology, especially any new language, because it gives you an opportunity to walk through parts of that language you might not otherwise touch. Our solution tonight is going to be extremely over-engineered to give us an opportunity to look at different pieces and parts of the Rust programming language. Now, earlier this week, I asked on the Northwest Arkansas Discord what you guys were interested in learning about Rust, and one of the biggest responses I got back was, "What is Rust?" Which is great. That's fine. It's either that or I've heard someone say Rust is awesome, but I don't know why, right? So let's see here. Can we pop my my screen on? There we go. So this is just the Rust homepage, and it tells us straight out of the box, Rust is a language empowering everyone to build reliable and efficient software. It's what's called a systems programming language. It has the performance of something like C or C++, but it gives you many fewer ways to cause yourself pain and anguish. One of the main quotes associated with Rust is that Rust is a language that gives you the hangover first, because there are some concepts to getting started with Rust that make the learning curve a little bit steep, and we're going to go over some of those tonight. But once you've got it, the bugs are so much easier to deal with. They're much easier to find. I can tell you from experience that my brief foray into C and C++ resulted in way too many instances of being like, okay, my program crashed, but I can't figure out why. And Rust doesn't do that. The compiler is great. Some of the things, and there's some whys in here. My biggest why is around performance. So, right off the top, I'm not a Rust programmer by trade. I'm a consultant. And I work in lots of different technologies. I do a lot of work around data and data analysis and data reporting, and for that, I use a programming language called R, which I won't say anything else about tonight. But R is a lot like Python in that it works great. It's got lots of tools, lots of special libraries and pieces of environment to work with data and to do a really good job of analysis. But it's also an interpreted language. It's got a garbage collector. It can be slow sometimes. And when you're trying to do something complicated with files that contain up to 5 million lines of data, then you've got to really worry about performance. So I picked up Rust so I could implement R code and R libraries in a lower level language that would help me speed up my code, help me produce tools for my clients that would work quickly and efficiently, and just be a good user experience. So that's why I've picked up Rust. There's some other reasons too. I know a lot of folks that I've come in contact with are JavaScript developers. And the great thing about Rust is you can do almost the exact same thing that I'm doing with R, with JavaScript and websites using WebAssembly. You can write code in Rust, compile it to WebAssembly, call it, build it with Webpack, call it with your JavaScript code, and run really complicated things really quickly using the Rust programming language. So that's what Rust is. That's why I care about Rust and why I think you will find Rust to be a really excellent tool. Rust also comes with a lot of excellent tools. The main one is Cargo, which is the Rust package manager. It's a lot like NPM. Cargo is a little bit like NPM plus ESLint plus every other sort of piece of software you have around a language all rolled into one. Okay, enough talking about Rust. Let's look at some Rust. Let me change my screen. All right, this is not Rust. This is just a terminal. But I want to talk through our problem, our piece of code that we're going to look at today. So let me bring that up real quick. So here's our code, and it does some things. One thing I'll point out is that we have tests in our code file. This is a pretty common convention in Rust to put unit tests right next to your code. And what we're doing is we're solving a puzzle where we take a string of characters, either dot, L, or R, and those strings represent a domino. I like pictures, so let's look at pictures. So let's say, for example, each of these lines of dominoes represents a string. This would be dot, dot, R, dot, 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 L, dot, dot, and then an R with some dots and an L. And your job is to look at this and say, okay, the R's are dominoes that have been pushed to the right, whichever way is right. The L's are dominoes that have been pushed to the left, and the dots are dominoes that are standing still. And each of those dominoes is going to fall. And at the end, you're going to have some result. You're going to have some dominoes over to the left, some over to the right, and some because they were pushed from the left and the right at the same time, or because they weren't pushed at all, will remain standing upright. So that's our goal. We're to take in a string. So in this case, we would take in for the top row dot, dot, R, dot, dot, and we would end up with dot, dot, R, R, R. Okay? So that's our puzzle. It's kind of fun. There are a couple of different ways to approach it. We'll talk about the way I did it because that's the way we're going with this. So here's what we're doing. We're taking our input string. This is a reference to a string slice in Rust, which just means it's a reference to a string. In Rust, makes a lot of use of references. References are kind of like pointers. It literally is that string over there. Go look at it. And it outputs a string. These are different. We don't have to get too much into the difference between the two. Just know that they are different sort of ways to look at a string. This is a string, and this points at a string. We start by creating a vector or an array that's as long as our input string that contains nothing but zeros. And that array represents the force on an individual domino, whether it's being pushed to the left or the right. To declare a variable in Rust, it looks a lot like declaring a variable in JavaScript. So we have our let command, and it's always let. There's no var or const. It's always let. And then you can optionally declare your variable as mutable. By default, all variables in Rust are immutable. You can't change them. You can't update them. You can't modify them. This is one of the ways that Rust sort of keeps your code safe, because Rust does an excellent job, and the Rust compiler in particular does an excellent job of watching out for mistakes that you might make and keeping you safe. And one of the ways it does that is by enforcing immutability by default. So we're creating an array, and in that array we've got a 0 for each of our dominoes that we've got on the input. At the beginning, that's our force on that index. Then we're also collecting, excuse me, we're collecting the characters from that string into an array. And if you pay close attention, my IDE here will point out to you the types of things at the end of the line. So this produces a vector of numbers. An I32 is a signed 32-bit integer, so positive or negative number. And this is a vector of characters. Rust uses vec the way that other languages would use list or an array where you can add things to and take away from the list. Rust has arrays as well, but those have to be a constant size known at compile time, which we don't know yet. We could get a string of any length. And this just turns it from a string into an array of characters. We start by setting the current force to 0. And then we loop through our string. So that's all this is doing, is we're starting out with the last index in our string. So we're going to start by moving from right to left. We're going to go backwards through our characters. And so that means we're moving to the left, right? We're moving from right to left. And so as we go, if we encounter a domino that has an R, we set the force to 0. If we encounter a domino that's an L, we set the force to the maximum because we're moving to the left. So we're calculating the leftward push on all of our dominoes. And we just put whatever the current force is into our force on index vector. We then check to see if the current force is greater than 0. And if it is, we decrease it by 1. So we'll never have a force less than 0. And then the rest of this just checks to see, okay, have we made it to the beginning of the string? If we've made it to the beginning of the string, break out of this loop. If we haven't, decrease the index and just go back 1. So we're going from the end to the beginning. And then we do it again. So we're calculating our forces going left. And so that gets us everything that falls to the left. And now we want to get everything that falls to the right. So we do the same thing. We reset our current force. We reset our index. We create a string to put our answer in. And then we take a while loop and we start at the left and we go to the right. And this is a pretty common pattern you see in a lot of languages. While the index is less than the length of the input, do this thing. And we're marching to the right. So if we see an R, we set the force to be the maximum. If we see an L, we set the force to be 0. And then we have this sort of complicated if statement that Rust is already complaining at us about with this warning. And we say, okay, if the force moving to the right is greater than, excuse me, if the force moving to the left is greater than the current force moving to the right, then we've got a domino that falls to the left. If the force moving to the right is greater than the force moving to the left, we've got an R domino. It's going to fall to the right. And if the forces are equal, then it's going to stand straight up. We do our same thing where we reduce the force each time. This is to indicate like the force kind of falling off over distance. So that if we have like, 2 dominoes on the end falling toward the middle ones will remain standing. And then we increase the index by 1 and we get our output. Okay. Whew. That's a mouthful. That's what our code's accomplishing. And from a high level, right, what we're doing is we are taking our string, we are representing dominoes in some kind of way. We are applying all the forces from the right to the left. We're applying all the forces from the left to the right. And then we're checking to see, okay, which one's greater. And that's what tells us what the final sort of state of each of those dominoes is going to be. That's not really a hard concept to explain, but man, it looks ugly in this code, right? So our goal tonight is going to be to take this code and remove as much from this function as we can by writing more Rust code and really just sort of abstract away some of the things that are just kind of confusing and hard to look at this code because if I wasn't sitting here explaining this to you, it might take a minute of staring and scratching your head to really realize what was going on here. So what I want to do is I want to take a look at this sort of side by side with itself. so we can see what we're changing as we go through our refactor. Okay, so this is the same thing we were looking at before. On the left-hand side, we've got changes that I'm making, and on the right-hand side, we've got the sort of the code as it was in its previous version. So the first thing I'd like to do is to address this warning that we're getting. Now, this warning is coming from the Rust compiler. Rust is a statically compiled language that, you know, it doesn't have an interpreter. You don't just write code and run it. You write code, you compile it, and then you run it. The Rust compiler can also run against your code as you write it and provide these helpful warnings. Rust errors and warnings are some of the most informative I've ever seen. And 9 times out of 10, they just tell you how to fix whatever you did wrong, which is great. In this case, we're getting a warning. It's not an error, but it's telling us that this if chain could be rewritten with a match statement. A match is like a switch statement's big brother. Match statements can be used for lots of things, and there are lots of really clever ways to use them. Today, we're actually just going to do a pretty simple, straight, like switch style statement. So the first thing I'm going to do is I'm going to import an object or an enum from the Rust standard library. You don't have everything imported by default in Rust. This helps keep your compiled binary small. And I just happen to know that this one lives in standard comp ordering. And an ordering is an enum that can have one of 3 different types. It can either be greater, less than, or equal to, which is, I mean, exactly what you'd expect to get from a comparison operation. Enums in Rust are super powerful, and we'll use some of our own in a little while. And they do lots of things, but one of the things they do really well is work with match statements. So let's put our match statement here. What we're going to do is we're going to match force on index at index. And we're going to compare it to the current force. Often you'll see Rust functions take references to items. This really just means anything that the function only needs to look at. It doesn't need to change or manipulate in some kind of way. It'll take as a reference. This helps speed up your code. And there are 3 possibilities here. There's ordering greater. And if the force on the index, which is the leftward force, is greater than the current force, which is the rightward force, then we're going to push out an L to our output. If it's less, we'll push out a right, and if they're equal, we'll push out a dot. There we go. And now we don't need this anymore. Good deal. So if you're paying attention here, you'll notice that the red line sort of indicates where we've taken lines away and sort of compares it to the right-hand side there. So we're just sort of looking at the diff between the 2 files. So this sort of helps see where we came from as we do our refactors. So that's one thing. Let's look at and I forgot to mention this, I have a to-do list at the top of all the things that I want to do to refactor this code. So the first thing on the list we skipped. We did the second thing already. We used a match statement instead of an if chain. The next thing we want to do is we want to replace these whiles and loops with just a regular for loop. I forgot to mention this earlier, but in Rust, a loop is literally just an infinite loop. It goes forever, and it will only stop if you break out of it. So not exactly what you want most of the time. So let's think about how we can use a for loop instead. So one thing we can do is we can just loop over the items in the string. We don't need to collect them into a vector if we're going to use a for loop. And we can actually get rid of the explicit declaration of the index here, because we're going to use this construct. We're going to say for index symbol. I'm using symbol instead of like character because char is the name of the type in Rust. It's a reserved word, so I can't use like char. So I'm just going to use symbol instead. In input, so that's our input. That's our string slice or our reference to a string. And then we're going to call a method on it called char indices, which returns the characters in the string and their positions, which is exactly what we want. And we want to go backwards, so we're just going to call rev or reverse. Now let's take a moment to unpack this line real quick. Rust makes copious use of iterators, and an iterator is just an object that takes some data in, it's an object that takes some data in and passes it back out one at a time. It can make transformations on it. It can do all sorts of things. If you're familiar with JavaScript, you can think of things like map, filter, and reduce that sort of take those Lambda functions and just realize that Rust has several dozen similar versions of map, filter, and reduce. And one of them is char indices, where it's returning both the index and the character at that position. Now that we've done that, and because we got rid of dominoes, we need to replace these calls to dominoes with the symbol that we got in, right? So we'll just say symbol. Oh. And symbol. And we're getting all sorts of errors down here, right? Because we removed our declaration for index. Because we removed it, we don't need these lines either. So that's good. We are really trimming this function down. We're going to do the same thing here and say for index and symbol in input dot char indices. Except this time, of course, we're not going to reverse it because we're going to move from left to right. And our last compiler warning is here. We don't need index anymore. Great. Now, to be honest, this is sort of my workflow for writing Rust code. It involves make a small change, fix all the compiler errors, then make another small change. Because the compiler is really your very best friend in Rust. It gives you really useful warnings and error messages and can help you fix them. Sometimes they can be a little cryptic if you're trying to do weird stuff, but for the most part, Rust sort of comes built in with this tutorial that helps you out in the form of its compiler. Now, the last thing I'm going to do is I'm going to run my tests again to make sure I didn't break everything. It should work. I don't have any compiler errors. So that gives me a lot of confidence. This is one of the great things about Rust. Rust code is pretty stable because the strictness of the compiler eliminates a whole host of errors that you might otherwise make that you just can't even run the code with those sorts of errors in there. If I tried to divide by 0 or something somewhere in my code, Rust will probably catch that for me before I ever try to run it. And we pass our tests. Perfect. So let's take a moment and just sort of see what we've changed. We've brought in the ordering enum. We've gotten rid of this dominoes line. We've removed some lines from our loops, turning them into into 4 loops, which are a little bit easier to read. And we've gotten rid of these calls to index. So we're just keeping track of the index in our loops. The other thing I'll point out is that this is a little bit like Python syntax. It's unpacking. So because this char indices returns a tuple that has both an index and a symbol, we can just unpack them into their individual component parts using this sort of syntax here. Just take a moment to let you take that in. And we can count our red lines here. 1, 2, 3, 4, 5, 6, 7, 8. So we've shaved 8 lines out of our function, and we haven't actually had to write any new structs or objects or abstractions of any kind. So that's a pretty good bit of progress there. All right, let's move on to our second pass. Okay, so this is what we ended up with before. You can take a moment to look at it and satisfy yourself that that's what we ended up with before. And now we have some more things on our to-do list, right? The first thing that we want to do is discriminate between a leftward force and a rightward force. And why do I want to do that? Well, 2 reasons. 1, I want to write my very own enum. And 2, it's a little bit tough just sort of looking at it to really tell the difference, right? So we've got some zeros for forces sprinkled throughout here. We've set, left to be I32 max and right to be I32 max. And so it's a little hard to tell the difference between those two. And I feel like it would be easier. It would be more readable if I could just look at that and go, oh, if we hit an R, we either want to apply no force or a maximum rightward force, right? Something that it just says that. So let's go and make our first sort of minor change here. I'm just going to highlight this area. And I'm going to replace all the zeros with a reference to an enum that doesn't exist yet. There we go. So we replaced all the zeros with a force none. And if we save this file, we're going to get tons of compiler errors, right? You see the little E's on each line. And that error is that you haven't declared the type force. I don't know what this is. Well, let's do that. Just to help me organize my thoughts here. So for a force, as I mentioned, we're going to use an enum, and declaring an enum is pretty simple. You just say enum and the name, and then what different types can it be? It can be a none, and this represents no force at all. It can be a leftward force with some magnitude, or it can be a rightward force with some magnitude. So this U8 here, this is an unsigned 8-bit integer that's, the range from 0 to 255. I don't think I'll need any numbers bigger than that, so I'm just using the smallest sort of unsigned integer type here. Important to note that you can associate values with enums, with enum types in Rust. This is extremely powerful because Rust's type system is extremely strict. And so this allows me to do things like if I want a function that can take maybe one type or maybe another type, I can use an enum and sort of wrap those two different types in my enum. Variants is what each of these are called. These are called variants. And so a none will have nothing associated with it. A leftward and rightward force will both have a value. How big is that rightward force? Okay, so let's save, and we can see that, hey, some errors went away. Some of them did not, though. One thing it's telling us is that our force does not implement clone behavior. Now, this is where Rust starts to diverge from other programming languages a bit. In Rust, composition is favored much, much more than inheritance. What that means is you're not going to see subclasses in Rust. You won't see the common pattern of like I declare an animal class and I give it some sort of some data and some behavior that's common to all animals. And then I also declare like a dog class that does all the animal stuff plus some dog specific stuff. Rust, instead of like taking big chunks and sort of breaking them down, Rust starts with small chunks and builds them back up. And those chunks are called traits. That is different types of behavior that you can sort of tack on to different objects and different things in Rust. You can attach that behavior to enums. You can also attach it to structs, which we'll see in a little bit, which are sort of like classes. And Rust gives you a convenient way to sort of tack on some of that default behavior to these things. And that's called a derive. So we're going to derive clone for our force enum. We're also actually going to derive copy at the same time. Clone and copy is behavior that allows you to just easily make clones and copies of your data. Cloning is a little bit more of an expensive operation if you have really small data types. And right here, we've just got the only thing in here are numbers. So those are easy to copy. If you've got big things like a vector or a hash map or something like that, it would only be able to do clone. So, okay, hey, we got rid of the error on line 20. So let's see what the next one is. It's a mismatched type, right? Now, one thing we haven't done is explicitly typed each of these arguments in our function. We haven't told the compiler explicitly that force on index, for example, is a vector of whatever's. In fact, you can see it, well, actually you can't see because I would need to scroll out more. This type hint here would indicate that this is a vector containing forces and not numbers anymore. Rust has guessed. It's looked, it says, okay, you put forces in this vector. This is a vector of forces. Problem solved. The only thing is you can't mix forces and numbers. Well, that's fine. So this was for the moving from the right to the left, moving leftward. We wanted to give it a maximum force. So we're just going to give it the maximum leftward force, and that is a force leftward. And we're going to give it the biggest U8 it can hold, which is a U8 max. Hey, got rid of that one. And the same thing is going to apply here, right? Except now it's a rightward force. And I'm sort of using these names as I talk about these things because that's how I think about them, right? I don't really think about it as like, oh, well, the number for the domino in this place. No, it's the force acting on the domino. That's sort of what I want to model. And so that's what I want my code to say. I want my code to say what I'm thinking about this problem and about this puzzle. And so that's where a lot of these refactors are coming in. So let's see here. What error do we have on this line? Something's wrong with force. Oh, we have a problem. We have a binary operation, which is a thing that takes a left-hand side and a right-hand side. And we're trying to use it on a force. You know what? Good news. We don't need to compare it anymore. Because force none is force none. So I'm just going to get rid of this. I'm going to get rid of it down here too. That'll fix that error. Take that, compiler. Great. Done. Well, not quite. We still have more errors. We have another binary operation that we can't do. This is the sub-assign operation. And in fact, like it tells us that, right? It's from standard ops sub-assign. And this is, again, the compiler telling us what we need to do in order to make our code compile. So let's read this carefully. It says the binary assignment operation minus equals cannot be applied to the type force. An implementation of sub-assign might be missing for work in progress force. It's telling us that we don't have the sub-assign trait. We don't have the sub-assign behavior for our force enums. And that makes sense, right? Like you couldn't expect Rust to just sort of magically know how to subtract a number from a force. We have to tell it how to do that. Fine, let's do that. So we know we need to use the std ops sub-assign trait. And typically, in order to use a trait, you have to bring it into scope. You have to import it from the standard library. Okay, so we're gonna use sub-assign, and we're going to implement this trait for our force object. A ton of work in Rust is implementing traits for objects, giving behavior to your different data structures. And this is no exception. And the way that you do that is you use what's called an impl or an implementation block. So we're going to implement sub-assign of a U8 because we're subtracting a U8, a number, from our force for a force. Now, this is it's sort of like an abstract method, right? And in fact, if I save now, we're going to get an error down here that's going to tell us that we didn't implement the trait items and that there's a function associated with this trait. Most of the time, there's a function associated with the trait because a trait is about giving behavior to your object. And this is no different. So we're going to implement the function sub-assign. And sub-assign takes two arguments. It takes a mutable reference to self. References are one of the places where people get tripped up in Rust a lot, especially on references versus mutable references. And the rule in Rust is that you can have as many references to an item as you want, or you can have one mutable reference at a time. This prevents data races. This keeps one part of your program from looking at a piece of data while another part is trying to change it. You can have as many pieces of your code look at a piece of data that's not going to change, or you can have one place in your code able to change a piece of data at a time. And that's what this is doing. It's taking a mutable reference to self, and self in Rust is like this dot in JavaScript or self dot in Python. And it's going to change itself. So it's going to change the force that calls this function. And we're going to pass in the right-hand side, which is going to be a U8. Remember, this is us trying to subtract a number from a force and set that to be the value of the force, subtract and assign. Notice that this part here, this is our function signature in Rust. And function signatures tell you almost everything you need to know to use a function. It's telling us that we call the sub-assign function. It takes a mutable reference to self and a number as an argument. If it produced any output, that would be part of the signature too. But it doesn't. It mutates self in some way. And the way that we can do that here is we can dereference self. So we can say the value behind that mutable reference equals the result of a match statement. This is where match statements start to get really fun. Not only can you match on different values, but whatever the result of that match is can be assigned out to something else. So we're going to try to match on what type of force self is, and that's going to determine what it is after we take some value away from it. So if force is none, then we're just going to give back a force none. You can't Can't subtract anything from a force none, no matter what the number is. If force is already none, it's going to stay none. If you have a leftward force with some value, then we can destructure that value. So the V on the left-hand side of this match is going to get passed into the expression on the right-hand side of this match. So we can return a force leftward of V, and we're going to call a method on this V. You can call methods on numbers in Rust, and we're going to call the saturating sub method. We're doing this because the number inside leftward is an unsigned integer. It can never be less than 0. So saturating sub just subtracts from V until it gets to 0, and then it stops. And we're going to subtract the right-hand side. And then we're going to do the exact same thing with the rightward force. There we go. So with this, we have given our force the behavior to be able to take values away from it. And I'm going to shrink my console just a little bit. I hope it will still be readable for everyone. But this way you can see the whole line. Okay. So now if we go back, we've saved. Oh, we got rid of almost all of the errors except for this one. Right. The method compare exists, but we're still missing a trait. This is one of those cases where the Rust compiler is actually leading us astray. It's telling us that it thinks we need an iterator trait implementation. And it's sort of kind of couching it in some language that maybe that's what you need. It's actually not. There's another trait that we need in order to just be able to do direct comparisons. And that trait is I think it is in ops. No. Oh, I'm sorry. I don't actually have to bring this one in. I think this one is part of the prelude. So we're going to implement sorting and comparison for our forces. We're going to be able to compare the two together. So first thing we need to do is implement ordering for a force. Same situation as above. We're going to do function. We're going to create the compare method, and it's going to take a reference to itself and a reference to some other thing that's the same as itself. So this is just two references to two functions, and it's going to return that ordering that we saw before, right? Because that's what we want. And the way this works is we're going to compare the sort value of the left-hand side force, and we're going to compare it to the sort value of the right-hand side. And where am I getting sort values from? Nowhere. I'm making it up. I'll implement it later. Now, this is complaining to us. It's telling us that equal is also not implemented. Ordering is one of those funny things. You have to actually implement like 4 traits to get ordering. I don't know why, but you do. We can derive partial, equal, and equal, but we have to implement order and partial order. I could try to explain why you need all 4 of these things, but honestly, I'd probably get it wrong, and we don't have time for that right now. And I'm going to call this self. It's going to return an option ordering. And we're going to return some self.compare other. I'm going to take a moment to point out this option ordering. This is Rust's answer to possible null values. In Rust, you can never have a null or a none or a nothing or an undefined. Some of the different ways that different languages do that. Instead, you can have an option, and that option can either contain some value or it can be a none. And the handy thing about Rust is because it's a type that has its own behaviors. If you've got an option of an ordering, then you have to do something with it as an option. You can't just pretend that it's the value and run into these errors where it's like, oh, well, none doesn't implement the behavior you want, or undefined is, you don't get those types of errors in Rust. This is one of the ways that Rust sort of prevents you from shooting yourself in the foot. Now, the last thing I'm going to do is figure out what this sort value is going to be. And for this, I'm going to implement behavior directly on the force. So I'm not implementing a trait. I'm adding a method to the force, to the force enum. In Rust, typically data and behavior are split. I mean, and you can see here, right? Like traits are just like free-floating behavior that we can grab and attach to any sort of object or structure we want. And in this case, we're attaching it just to forces. And so that is a sort value self. And it's going to return a U8 because U8 seems like good enough. And that's what's inside the leftward and rightward forces. So what's the sort value? Well, if it's a none, we're just going to get back a 0. And if it's either a leftward or a rightward force, then we're going to return V. And the star that you're seeing here is the dereference operator. It turns a reference into a copy of the data that is being referred to. Let's see. Oh, I left out my match statement. That's embarrassing. I bet that was really confusing to watch. Like, why is he doing that? There we go. And so this does a few things for us. This allows for no force at all, and we are being able to compare our forces directly. Now, I know what you guys are thinking. There's a lot left on this list, and it's 7:18. We won't get to all of that, but we will run our tests to confirm that what we've done so far still works. There's a lot left to do here, but I want to give you a sneak peek at which direction this is going in. I'm going to put this code up on GitHub so that everybody can take a look at it, and we'll post the link in the Discord. But let's just see where we wanted to end up. We'll go from our first pass. There's actually a fifth pass. So our final function call is this single line here, where we take our input, we turn it into dominoes, we apply forces to it, we turn it back into symbols, and then we collect it into a string and return it back to the user. And to do that, we created dominoes. We implemented a whole bunch of stuff for forces. And did all sorts of other fun things. Now, one thing you'll note is that Rust can be fairly verbose. You write a lot of code, but hopefully you can figure out ways to make what that code is and what it's doing very clear for your users. And with that, I think we will stop and go to questions. Let's see here. Okay, so I see a question in the comments that says, "How long did it take you to master Rust?" It took me exactly as long to master Rust as it has taken me to master any other programming language that I happen to be able to write, which is I have not done it yet. I have been working with Rust since probably about February of this year, off and on, for a couple of different projects. So once you get over the initial hump with Rust, it's really easy to get going. I mentioned at the beginning, right? Like Rust is a language that gives you the hangover first. There are a couple of concepts that can hang up a programmer who's new to Rust. Borrowing and ownership is one of those. The idea of like breaking up traits. And using composition if you're used to object-oriented stuff. Then once you're past that, though, a lot of it is really straightforward. So it says, is Rust object-oriented, functional, or both? So Rust it's a little bit of a mix of both. I mentioned before, and I didn't get a chance to show them, Rust has the idea of structs as opposed to classes, which is like just the data part of a class. And you can compose with those classes pretty well, adding and attaching behavior to those. I use a lot of like object-oriented types of things in Rust because one of the things Rust does for you, it's part of it's kind of the Rust promise, is what they call zero-cost abstractions. So you can write all of these classes and things like you saw me doing. You can, instead of passing a number around, well, that number represents a force, so I'm going to make it a force. And that costs you nothing in terms of performance of your code. Your code will run just as fast because the compiler will produce the same machine code for the computer, whether you use those abstractions or not. So it's normally in your best interest to use them because it makes your code much more readable and much more maintainable. I see a question. So in languages like C++, you have to work with memory allocations and the like. You find yourself doing that a lot with Rust, or does it do it for you pretty well? I do not do memory allocation ever. I do not do memory freeing ever when I write Rust code. You can, but to do it, you have to explicitly wrap it in what's called an unsafe block. The reason that ownership and borrowing can be a little bit difficult at the beginning is that it makes you write your code in such a way that the Rust compiler can handle all of the memory allocation and memory freeing for you in a safe way. So as long as you do not explicitly create an unsafe block and start like doing stuff with pointers and allocating and freeing memory inside that block, you should never run into things like, double free, which is a thing you get in C++ a lot, where you free a piece of memory and then later on you try to free it again, or read after free, where your program freed some memory, some other program on your computer probably wrote to it, and then you go back and try to read from that piece of memory again, and you get like, Lord only knows what can happen at that point. Those are I won't say impossible, but they should never happen unless you're explicitly writing unsafe Rust. I'm not nearly enough of a Rust expert to do a lot of unsafe Rust. It scares me, but it's certainly there. You can do it if you choose to. If you can figure out a way to, like, if the compiler really is slowing you down and you need to do something it doesn't want you to do, you can do that. But in general, Rust handles all of your memory allocation and cleanup for you. That actually rolls into the next question I see, which is asking about Rust and garbage collection. Rust does not have a garbage collector. This does a couple of things for you. One is it makes your code extremely reliable. So one of the things that I've read about and heard about is how people are using Rust to create APIs for especially like streaming services, because there's no garbage collection cycles in the running of that code. And if you're not familiar with garbage collection is just like it runs inside your code, and it goes through and it cleans up all of the extra references to things that you're not using for you. And that takes CPU time in general. That's time when your code is running that it's doing something other than the code you wrote, doing other than solving the problem that that you wrote it to solve. And for especially like streaming applications, this can cause hiccups. This can cause inconsistent behavior. And so if you're doing like really performance sensitive stuff, just the fact that Rust does not have a garbage collection can really help you out with performance and consistency and reliability. You know, I think as I mentioned at the beginning, right? Like Rust is really great too, in my opinion, for an incremental language. So often behavior in higher level languages like Python or R or Ruby are implemented in some lower level language like C or C++ or even Fortran. And if those sound scary to you, then they kind of sound scary to me too. And Rust gives you an option to write code that runs like those languages, but with guardrails in place. It's sort of like bowling with the bumpers up. All right. If you've got any more questions, feel free to throw them in the chat. Otherwise, I'm just going to like talk about random stuff. My text editor. So I'm running NeoVim actually, which is a flavor of Vim. It's got some nice support for language server protocols, which is the same thing that VS Code uses to do things like type hints and syntax highlighting and things like that. So that's where all of the like the types out to the side and where the compiler errors showing up in my text editor came from. That was actually from a program that's sort of packaged with Rust. And I didn't mention this before, but Rust installation is super easy. If you go to the Rust website, there's like a shell script that you just run, and it downloads and installs Rust on your machine, along with cargo and a lot of other things that you need to make Rust run. One of those is Rust Analyzer, which is the thing that was producing those error messages for me. It runs on your code. When you save your file, it goes ahead and runs and analyzes your code and spits back out. It basically says, hey, this is what the compiler is going to get you for if you've got errors. And so, again, it really, really helps with the Rust workflow. I've probably learned more about writing Rust through just like breaking stuff and obeying the compiler on how to fix it than on anything else. I am running Linux. I'm running Fedora 34 right now. You know, at some point I started dual booting Linux with Windows, and I still have my Windows partition that I occasionally boot up for video games, but that's about it at this point. Gotta love that Linux life. Part of that Linux life is earlier today I had to write a shell script to do a thing that I probably would have been able to do with an actual like nice user interface on a Windows machine or a Mac, but I got to write a shell script for it, so I have that going for me.
I was starting to wonder if I was going to be brought back in here. So thank you so much, Eric. It was really cool, really informative. And I had no idea about the garbage collection. I just have heard stuff about Rust and garbage collection, and or mentioned, the two, and so it's really cool to hear that it doesn't have it at all, right? But so thank you so much for taking your time to speak today. It was really informative and great. And I just wanted to real quick thank anybody who showed up and watched, or anybody who's watching later here on YouTube. And just want to speak about some of our upcoming events. Every Wednesday from 6:30 to 7:30 Central Time, we meet and we have a meetup. The schedule is on our website. We have a lot of cool ways to get your hands into real world projects going on right now. You can reach out to me or to Miguel, and we have tons of plans for and ideas for different things to build around the community. It's a good chance to really get in the workflow with the team and to get real world experience in a lot of different areas. But as for that, we're going to go ahead and be respectful of everybody's time and wrap it up.
All right. Thank you guys so much for having me.
No, thanks for coming. We appreciate you.